Science provides us with many instruments of great precision to look into the workings of nature. Over the centuries, many scientists have come up with lots of different laws and results and theorems placed one on top of other to explain and to predict various natural phenomena. However, there is always a limit what all those results put together can achieve. And beyond that, we have the world of unpredictability. In order to understand the behavior of real gases, physicists postulate the existence of what is called an ideal gas, a hypothetical object that behaves nicely in a mathematical way and yet provides a good approximation to how real gases behave in nature. Similarly, in order to explain unpredictability, to deal with this unpredictable world, statisticians postulate something which may be called the ideal form of unpredictability. An unpredictability that is in a way predictable. Statisticians call it a random experiment, like a coin toss. Whether it is going to show head or tail is unpredictable, yet I can predictably repeat this process and say that its unpredictable behavior will predictably repeat itself. The behavior that I saw during the first coin toss is also the same behavior that I am going to see during the second coin toss. Such ideal, predictable unpredictability is called a random experiment by statisticians. Another example of such a behavior is that of a die. If I take a die and I try to roll it, then it shows either 1 or 2 or 3 or 4 or 5 or 6. Now it is not possible to predict which of these is going to happen. That is quite obvious. But when I say that rolling a die is a random experiment, I make a more technically precise assumption. We are saying that whatever is the underlying process in the die which we cannot understand, the thing that gives rise to its unpredictability, can be repeated in a predictable way. It is this fact that is captured in the statement that a die roll is a random experiment. Indeed, random experiments are the most fundamental objects for a statistician. Just as a chemist tries to explain the workings of the universe based on the hypothetical behaviors of the molecules and atoms and subatomic particles, similarly, a statistician tries to explain the entire unpredictable nature as a combination of various random experiments, this ideal unpredictable setup. So when a statistician is confronted with an unpredictable natural phenomenon, he tries to approximate that with various random experiments connected using intricate mathematical relations. All these things together is called a statistical model. The reason why statisticians love such ideal unpredictable behavior, these random experiments, is a concept called statistical regularity. Roughly speaking, it means the following. If you take a random experiment and repeat it a large number of times, then under certain conditions, the overall behavior of all these random experiments, the sum total, somehow in the long run loses its randomness. It becomes more and more regular. This is something which is not exactly our everyday experience. When we see lots of randomness put together, we are more likely to expect that the resulting thing will be even more random, more chaotic. But there are certain situations where lots of randomness piled together under certain conditions will lead to a behavior which is more regular than the individual random experiments themselves. For example, if I take this particular die and roll it a large number of times, then if I plot the proportion of times I get a 6 with the number of die rolls that I have made, then this plot will converge, will become flatter as time progresses. Initially it will be a lot of jumps, so that is the case where you are seeing the randomness. Eventually it flattens out. That is what says that things are getting more and more regular as you are piling more and more die rolls one on top of another. That is statistical regularity. The idea of statistical regularity is like a seed. From this comes two different methods by which we can attack various unpredictable phenomena of nature. The first is the naive one, namely, once you have a statistical model, simply keep on repeating the various random experiments in it a large number of times and wait until statistical regularity sets in. The other technique is to find the limiting behavior mathematically without actually carrying out any of the random experiments. The first approach is laborious. It requires performing lots of random experiments. But the second approach, thanks to various brilliant mathematicians like Kolmogorov, Bernoulli, and many others over centuries, have given rise to the important branch of mathematics that we now know as probability theory. Over the centuries, it has offered us lots of different mathematical gems. We have the laws of large number, the concept of consistency, central limit theorems, Markov chains, ergodicity, martingale convergence theorems, to name a few. However, most of this development was motivated by mathematical problems. So there were interesting, challenging mathematical problems far removed from the original practical intentions, and probabilists have been chasing such mathematical problems over centuries. As a result, practical problems continue to suffer because even the most complicated probability theory falls far too short of catering to the need of even a simple real-life unpredictability problem. The lopsided development of the statistical tree, with hardly anything on this half and lots of useless mathematical result on the other half, irritated many applied statisticians. They did not want nice mathematical results. They wanted some tools that could be used to explore statistical models of any practical importance. For that, they started to explore the first half, the neglected branch. And for that, they used the computer. What follows is an interesting story that weaves between statistics and computer science, we shall cut a long story short by presenting the entire development in the form of a little fairy tale. Pretend that Dr. A is a busy scientist and B is an idle man. A wants to follow the first branch of the statistical tree and for that needs to toss a coin 100 times. She outsources the job to B. B sees a business opportunity. Soon he gets many clients. In fact, too many. He finds it hard to cope with the rush hour demand and he starts tossing yet during the dead of night to create a backup list of tosses. After doing a few trillion tosses, B has another idea, a mischievous one this time. He stops tossing and starts recycling. So effectively, he has turned his long list of tosses into a circle and he keeps on going round and round the big circle, hoping that nobody would notice. This story may sound silly, indeed it is a silly story. However, this does give us an important fact about how computers generate random numbers. Inside every computing system, every language like C or Java or software like R or MATLAB or Octave or Scilab, there is one such big circle of random numbers built inside. That is a fixed circle. Every time we want random numbers from the computer picks up one position in that big circle randomly, or I should even say in some unpredictable way, typically based on the system clock, and then hands out the appropriate number of those digits as the outcome of random experiments. So strictly speaking, these are not truly random because the same set of numbers, the same circle of numbers is being used again and again. However, since the circle is very large, we hardly see its effect in most day-to-day random number generations. So precisely, people would like to call it pseudo-random number, but for practical application, it is as good as carrying out exact random experiments. The story that we mentioned about generating random numbers worked with only coin tossing. Now there is a result in statistics which allows one to generate all sorts of random experiments using only random numbers generated from the uniform distribution. This video is not the place to go into that theory, but suffice it to say that we can use the same technique, the same cycle of numbers to generate random numbers from any given distribution. Now we are going to take a look at one practical example where we can use random numbers to our advantage. The main idea is this: you will be given one particular situation, a real life situation, and we shall create a statistical model of it. That is, we will convert that unpredictability to something which can be expressed in terms of those random experiments, those ideal unpredictable objects. Then we shall use the computer to generate random numbers for us from appropriate distributions and actually carry out that natural process inside the computer and learn about its behavior. Imagine that there is a particle counter and particles are hitting it at random time points. And our aim is to estimate the rate at which those particles are hitting it. As the particle counter is working, the data that we are getting are the hit times. Every time a particle hits the counter makes note of the time point. So our data consists of all the time instants when a particle hit the counter. Equivalently, we can say that the inter-arrival times, let's call them xi's, those are what constitute our data. Now we need some kind of a statistical model which will relate these xi's with the rate that we are trying to estimate. And one popular model is to assume that the xi's are IID exponential with rate lambda. This is also equivalently formulated as a Poisson process. Standard statistical theory suggests that we should use the maximum likelihood estimator for lambda, which is lambda hat equal to 1 over the average xi's. This stands to reason because if the rate is high, in that case the points are coming quite thick. As a result, the inter-arrival times are small. So whenever average of these xi's, x bar, is small, we suspect that lambda is high. So we can naturally choose lambda hat equal to 1 over x bar, which also happens to be the theoretically justified estimator. Now that was the ideal scenario. The scenario that you can deal with quite easily using textbook statistics and probability theory. But real life is far more complicated. In particular, our counter has a problem. The problem is that every time a particle is detected, the counter gets jammed for 1 second. So once a particle is detected, if another particle comes within 1 second of that time, then that second particle will not be detected. After this jam period is over, the counter again starts detecting fresh particles. So again, our data set consists of those inter-arrival times, or now I should better call them inter-detection times. I will call them xi's again. Our problem remains the same as before. We want to estimate lambda. And the question is lambda hat equal to 1 over x bar still a good estimator or not? This little real-life particle counter is already beyond what we can tackle using our usual textbook statistics and probability theory. So let us see how we can use simulation to solve the problem. Now when we do simulation, our aim is to build up the entire process following the statistical model. We start with the random experiment, then combine them using the model to arrive at the data. So the process is usually the opposite of the process in which we have collected the data. When we collected the data, we first observed the hit times, then we took the differences to get the inter-arrival gaps. However, when we specified the model, we started by modeling those inter-arrival gaps as IID exponential. So the random experiment lies in those inter-arrival gaps. So when we are going to write a computer program, then we shall start by creating those inter-arrival gaps, and then we shall take the cumulative sum to get the hit times. In order to implement this idea, we need some kind of a computing system, and the computing system that I am going to use is R. It's a free computing environment. So in order to follow this example, you should download and install it in your machine. It is available for all sorts of platforms. not very difficult to install. However, it does have a little learning curve, and I am skipping that initial part. So if you already know R, you will be following quite easily. If not, there will be certain things which will not be completely clear. However, the code will be more or less self-explanatory. Some of the syntax details you can always look up later using Google. So let's get started. We have the inter-arrival gaps that we are going to prepare. So I will call them gaps. So I will write gaps equal to, and I will make them random numbers Rx. Rx is the function that creates random numbers from the exponential distribution, and I will say how many times do I want? Suppose I want 1000 times. So 1000 particles. And I will give it some rate, so I will make rate equal to, well, something, I will say call it something, I will call it lambda. Now I am going to put the true value of lambda later. So for the time being, I just write rate equal to lambda. Okay, now from this, I have to get hold of the hit times. So I will call them hits, and hits will be simply cumulative sum that is computed by cum sum caps. So this is the cumulative sum of the caps. Now comes the difficult part. We have to find out which of these hits are going to be detected. For that, I will go down this list of all the hits. I will use a for loop for this purpose. For, well, I will call it T, for T in hits. So I have a list of hit times which I have stored in hits. So for T in hits, what I will do is, I will try to find out whether this is stored or not. I will check whether this time T comes after the jam n. So jam n is going to be variable. So if T is after jam n, then definitely it is going to be detected. So I will write detected hits will now take this into account. So det hits T. So let's quickly understand what this means. This means that I am taking a list of detected hits, the list that I am actually constructing, and then with it I am appending yet another type. So C is the function which appends. That is, it takes a list and at the end it adds yet another element. In fact, you can also append one list with another. C stands for concatenate. So detected hits, with detected hits, that's like a bag of numbers. With that bag, you add, into that bag, you add yet another number, which is T. And then you also update the jam end. Since you have detected it, so the jamming starts again. So T plus 1.0. 1.0 is the duration during which it will remain jammed. And that is the end of this if. Now what I have to take care of in this case is that I have to now figure out what is the detected hits list, and for that I will create this thing detected hits. Initially it's just an empty bag. When I write C open bracket close bracket, this says it's just an empty bag, and then I also have to specify the initial jam n, which is 0. So I assume that the machine starts in an unjammed state. So the jam end was at 0. So the whatever jam was earlier, it has ended by the time 0. So it starts out without any jam. So after I come out of this for loop, I now have my detected gaps. So dead gaps. No, I have my detected hits. I have to compute the detected gaps out of it. Now that I have my detected hits, it is easy to compute the detected gaps by merely taking the successive differences. So it is difference of the detected hits. I now have to find my lambda estimator. Lambda estimated and I am going to maintain a list of them. That is going to be, so I will call it lambda estimate first, which is 1 by mean of these detected gaps. So I just applied my usual formula, the reciprocal of the average detected gaps. I call it lambda est. Now I am not going to get only one such value. So whatever value of lambda I put in, I will get a value of estimated lambda. So let me just try it out. I will give it some value of lambda. Initially I have left it blank. Suppose I give it the value, say 0.5. So here I am playing God. I am saying as if I know, because I am creating my data. I set lambda equal to 0.5. Then using that I am creating my gaps. From that I get the true heating times. And then I use this mechanism here to find out which of the heats are detected. Based on that I compute the detected gaps, and finally I apply my textbook formula for lambda estimate. So let's just see how it behaves. I will run it. So I have run it. I have run it. So I started with lambda equal to 0.5, and let's see what I get as my lambda estimate. I get 0.325. So I can see that I have got an underestimate, which is natural, because after all I am detecting things at a rarer time interval. So I am not detecting certain things. So let's take some other value of lambda. Suppose I take lambda equal to 5. So lambda equal to 5 means things are coming very fast, thick and fast. So let's try. So now I have my lambda est 0.83. Oh, that's very bad. So even though my rate is very fast, so it is getting jammed most of the time. So it is hardly detecting anything. Okay, let's try something else. Let's try something 0.1. So if you use 0.1, this means the rate is very low. So the particle heats are few and far between. Let's see what happens now. So I will try lambda est, and now I find that the lambda estimated lambda is pretty close. It is 0.09, because since all those heats are few and far between, so hardly two things are within 1 second of each other. So you hardly feel the effect of jamming. Now of course if I take different values of lambda and keep on doing things like this, that will get pretty boring soon. So what we want to do is that we want to make a plot. So for that, instead of taking a simple value of lambda, I will take a list of values. So I will call it lambdas. Lambdas, I will make a sequence 0.1 to say up to 10. And how many values do I want in that? Length, abbreviated to length. Length will be say 100. So I take all these lambdas, and then I put this. I will take lambda from this list. So I will write for lambda in lambdas. So I put this entire thing in a loop, and then again my lambda estimates. Now I should not get a single estimate. For each different value of lambda, I should get one value of estimated lambda. So I should call that also lambda estimates. I put an S, and I need a list, and every time I go in that loop, I have to add one more estimate to my list. So I will use again our familiar frame, the concatenate function, lambda estimates, and I will add that 1 over min formula to the end of my existing list. Now whenever I do that, I have to remember to create my list. So I will have to create my lambda estimates as my empty list. So now at the end I get not just a single value of lambda, but a list of lambda. So let's try to see what we get, and I have done that. So let's take a look at my lambdas that I used. Oh, I see. Oh, I should look at lambdas. And these are all the values of lambdas that I've used, starting from 0.1 going all the way up to 100, all the way up to 10, and I have 100 values. These little square bracket things at the left will tell you what the numbers are. For example, this number is the 91st number, 92nd, etc., going all the way up to this, 10. So let's now see what are the lambda hats that have lambda estimates. I call them lambda estimates. And these are the estimated lambdas, too many numbers. So let's make a plot. Okay, I will put the plot in my script file. So whenever you use R, it's a good idea to maintain a script file so that you can reuse the codes. So I'm going to make a plot, that's a line plot. So you write down the x values as the first argument, the y values as the second argument. So I'm plotting lambda in the x-axis and all the estimated lambda in the y-axis, and by default it will make a scatter plot. I want a line diagram. So I write tie equals line. Tie is the abbreviation of type. If you want, you can make it type. And let's take a look at what plot I get. So here's the plot that I get. And you can see that as lambda increases, the lambdas increase, the estimated lambdas do not increase at the equal pace. Initially they were increasing, but eventually they are sort of flattening out, which is expected. Now you see all these jagged things. The jagged things are because we are taking only one simulated case for each particular value of lambda. Now you may say that, well, I will do it again and again. After all, the entire idea behind simulation is that we are using statistical regularity. So why not do the entire process multiple times? That's quite easily done. For that, what we have to do is this. We will just carry out this experiment for, say, 100 times. For each value of lambda, this entire experiment, I will be carrying out this from lambda to lambda estimate. I will be doing it, say, 100 times. So I will do the following. For I in 1 to 100. Inside that, I will generate my data, the gaps, then the hits. Then I will work out the detected hits, and I will work out my detected gaps. Then based on that, I will also compute my estimated lambda. I will put that in a temporary variable. So I will put temp ctmp, and I will take this formula and I will put it here. So now I create a temporary thing, and when I come out of this, I have a list of estimated lambdas for all these things for the same value of lambda. So my estimated lambda, I will take mean of these 10. So I am taking the average, and whenever I do that, we should remember to create TMP as the empty list initially. So let's understand clearly what we are doing. We start with a grid of values for lambda, and we take an empty list of the estimated lambda. Then for each lambda in that grid of values, I am first creating an empty list to store the various lambda hats. Now I am creating the data, and I am computing the estimated lambda hat for that particular value of lambda. Keeping the value of lambda same, I am repeating the process 100 times so that I get a better estimate of lambda hat. Then I take the mean and store that as my estimated lambda. When I come out of this big loop, I now have all my true lambda values, which I know because I have simulated using them, and my estimated lambdas. Now I am going to make the plot. So let's see what I get. Now my plot is somewhat more smooth, not much smoother because I have done only 100 times. You can increase the number, then you will get even smoother things, but it is somewhat smoother than before. In fact, if you want, you can also have error bars. Simply, instead of computing only the mean, you can also compute the variance. In this way, you can do whatever you like with all those estimated values. While simulation is a very powerful technique and it is getting more and more popular every day, there are some people, typically old-fashioned people, who are still quite uncomfortable, somewhat uncomfortable with the idea of simulation. They would still prefer to work out complicated probability theory results instead of carrying out a computer simulation. Now, the main reason why they feel uncomfortable is that when they think about computer simulation, they consider it in a somewhat wrong fashion. So let us understand how computer simulation fits with our usual probability theory. Both probability theory and computer simulation starts with statistical modeling. We start with the statistical model. And in order to make use of any statistical model, we have to use statistical regularity, repeating the random experiments a large number of times to get rid of the random variations to some extent. In case of computer simulation, we are carrying out these random experiments directly. In case of probability theory, we are approximating them with the limiting behavior. So we are trying to find out the limiting value. But we must understand that in real life, it is not the limiting behavior that we are interested in. We are interested in the actual finite sample size behavior. It so happens that the computation is very difficult. That is why we go into that limiting behavior. So probability theory itself is nothing but an approximation. It is true that we use exact mathematics to carry out all those probability computation, but the final quantity that you get, that is only an approximation of what we are going to observe in practice. In that sense, computer simulation and probability theory are two parallel ways of making use of statistical regularity in the context of statistical modeling. But the old-fashioned people who generally are against statistical simulation wrongly think that the situation is this: you start with statistical regularity, statistical model, then you convert that into a probability problem and you further approximate that probability problem using statistical simulation. So for them, statistical simulation is a second order approximation. That is not true. We are not trying to find out the limiting value that probability theory would give us. That is not our aim. We are actually carrying out the random experiment itself to see how it behaves. These are two parallel ways. These are two sibling techniques. One is not coming under the other. So it is not a second-rate approximation to statistical model. The wrong idea usually comes like this. You have some kind of a statistical model that you can work out using probability theory, which means you can approximate that using probabilistic limit computations. And then you also carry out simulation and you find that these two results are quite far apart. And then you think that the probability computations are the computations, the actual value, and these things are far from that. So, at least in this example, I can see that the simulated thing is not giving me the correct answer, because they wrongly believe that the probability results are the correct answer. You must understand, we do not know what that correct answer is. The probability values themselves are nothing but approximations. When I say I am going to toss a coin 1000 times, the probability that the coin shows head is equal to half. That itself is a limiting approximation. And you must not think that that half is a very true value sitting somewhere inside the coin, and by simulating we are actually getting an approximation to it. It is just a random environment, and there are two ways we are trying to approximate it. They are two parallel methods, not directly comparable. True comparison between probability theory and computer simulation will be possible only when we take a real life problem and try to solve it or approximate it using both these techniques, and then compare the final result not with each other but with the outcome that we get when we apply them to the real life situation. Whenever we have a real life problem, naturally there is some kind of a loss that we have in mind. So these techniques, both of these techniques will suggest certain strategies. So use this strategy and also use that strategy separately and see which strategy leads you to success. Unfortunately, if such a thing is done, they are not done very often. But even if in those limited situations where such things have been done, the general situation is this, that the weakest link in the entire procedure is the statistical modeling part. It is very difficult to model real-life unpredictability in terms of those ideal random experiments. When we do that approximation, we usually deviate a lot from real life, and that is the weakest link. So the reason why both probability theory and computer simulation typically fails very badly for real-life problems is because the statistical modeling, which is common to both these approaches, that itself is rather weak. But other than that, there is not much reason to choose one over the other, except that computer simulation is far more general. You can apply it without going deep into some mathematical analysis. But other than this, there is no reason to choose one over the other. And in fact, as long as you do not care about your real life applications, as most people do not, and your main aim is to get published and getting tenure positions and things like that, it is seen that computer simulation is just as good as doing probability computations.